Number one, a very important piece of information is that FAD is parallel to line segment EHC. So I'm going to put little arrows to indicate that they're parallel. And that's super important because when we have parallel lines, they're usually cut by a transversal, and then we have a ton of angle relationships that generally exist. When parallel lines are cut by a transversal, we have alternate interior angles that are congruent, we have corresponding angles that are congruent, alternate exterior angles that are congruent, same side interior angles that are supplementary. All we have to do is figure out what we're working with here. So let's mark the diagram and figure out which of those angle relationships is going to help us reach our goal. So angle FAB is 48 degrees, right in there. FAB inside A. Angle ECB is 18 degrees. ECB right in here. And then we are looking for angle ABC right in here. I'm going to just put a question mark. That's what we're looking for. So what I like to do when we have parallel lines is I like to highlight the parallel lines and the transversal connecting them. And I'm always looking out for my letter Z because I really like when we have a letter Z, because when we have letter Z, we have alternate interior angles, and alternate interior angles are congruent when parallel lines are cut by a transversal. So in the corners of the Z, we have our alternate interior angles. Now we have two angles of this triangle, and all three angles of a triangle always make 180 degrees. So what I can do is I can do 48 plus 18, the two angles of the triangle, and that is 66. And then I can subtract 66 from 180 to get 114. So 114 is the last angle of the triangle. That looks really bad over here because I'm trying to write in a small space, so I'll just draw an arrow. And now this angle, angle HBC, and this angle, angle ABC, are supplementary. They form a linear pair. So if this angle is 114, then 180 minus 114, that is 66 degrees. And that's the angle that we're looking for, angle ABC, so that is 66 degrees. And number two, we need to find the length of line segment BC, which is labeled as D. You have two options. You have a right triangle, so you can use trig, but I have two sides of the right triangle, so I'm going to use Pythagorean theorem. D is the hypotenuse that we're finding, so to do Pythagorean theorem, I could just do 1.5 squared plus 1.5 squared equals, I'll just use D squared instead of C squared because it's D. Let's see what 1.5 squared is. I'm going to show you guys my calculator. $2.25. So then we need to do 2.25 plus 2.25. And that's 4.5. And then to get D by itself, I'm going to take the square root. And that's about 2.12, which is answer choice number 4. For number 3, line segment CD is the altitude drawn to hypotenuse EF in right triangle ECF. Always draw a picture. ECF. CD is the altitude drawn to the hypotenuse EF. So the hypotenuse is EF, I have that labeled correctly. And CD is drawn to the hypotenuse. And it's an altitude, so it's a perpendicular line creating right angles. So what we have here is we have a situation where we have a big right triangle with an altitude creating two smaller right triangles inside of it. Now, remember, whenever you have the situation, the big right triangle and the two smaller right triangles on the inside are similar. But the problem is it's difficult to see what corresponds to each other, what sides correspond, because right now all three triangles are facing different directions. So I'm going to redraw all three triangles so that way we can make them face the same direction. And for all of them, I'm going to put the right angle over here. So the big one, I'm going to just keep the same. The big one doesn't matter. And then the two smaller ones are going to be based off of the big one. Let me do first this one over here. So the right angle's at D. And now I'm going to think about what this triangle shares with the large triangle. And it shares angle E with the large triangle. Angle E is in this triangle. At the same time, it's in this triangle. So due to the reflexive property, it's congruent to itself. So it has to correspond in the similar triangles. So since I put E over here in the big triangle, I have to put E in the same spot in that triangle. And that leaves C to be over here. Now I'll do this triangle. Once again, the right angle is at D. And I'm going to think about what this triangle shares with the big triangle. And it shares F. F is an angle of the small triangle. And at the same time, F is an angle of the large triangle as well. It's shared. It matches up. It corresponds, reflective property. So since F is over here in the big triangle, F needs to be in the same spot over here because they match up. And that leaves C to be over here. So now I'm going to label EC is 10. And I could have labeled at the beginning, but it doesn't matter. And EC appears in two spots. EF is 24. See, it's so much easier to see here when I separated the triangles. Because like here, like that's hard to see. And we need to find ED. That took me a lot of time to find ED. So I see the two similar triangles that we need to focus on are these two. Because we don't have any information about this one. So now I can really easily just like set up a proportion. So I'll do 10 over x, they correspond. And 24 over 10, they correspond, super easy. The hard part is really just redrawing those triangles. And then you're good to go with your proportion. Let me do 100 divided by 24. And that's about 4.2. In an equilateral triangle, all the sides are equal and all the angles are equal. So all the angles measure 60 degrees. We're talking about the height. Height is another word for altitude. Perpendicular line, top to bottom of the triangle. And in an equilateral triangle, the altitude does something really special. Splits the angle. It's an angle bisector. And it splits the side equally into two congruent pieces. It is a bisector of the side as well. A perpendicular bisector, we can say, because it's perpendicular and it bisects. We need to find the perimeter of this triangle if the height is 2 radical 3. We have a 30, 60, 90 triangle. So what I'm going to do here is I'm going to use the ratio for 30, 60, 90 triangles, which is 1 to radical 3 to 2. This is the smallest side, middle side, biggest side. You can find the smallest side because it's across from the smallest angle. So for example, here's the 30-degree angle, the smallest angle. Opposite from that, which would be the side over here, would be the shortest side of that triangle. And it makes sense because the hypotenuse needs to be the biggest side. Here we have the shortest side. The hypotenuse across from the biggest angle, the 90-degree angle, is the biggest side. And since the 60-degree angle is the middle biggest angle, the side across from the 60-degree angle is the middle biggest side. So we're given here the middle biggest side to work with. We're given the radical 3 part of the ratio. What we need to do is we need to get back to the 1 part of the ratio. Oop. Okay, so to get to the 1 part of the ratio, we're going smaller. So we need to divide. And we're going to divide by radical 3. So all I'm going to do is take 2 radical 3, and I can do it, I'll do it right down here. Let me just get a little bit more space. So let me take that 2 radical 3, and I'm going to just divide it by radical 3. Radical 3 in the top and bottom, they cancel out. So the 1 part of the ratio is simply just 2. And then if I wanted to get from the 1 part of the ratio to the biggest side, to the 2 part of the ratio, between the smallest and the biggest is a 1 to 2 ratio. So the small side is doubled. So 2 times 2 is 4. And now I know all the sides. The smallest side is 2. The biggest side is 4. We need the perimeter of the equilateral triangle. 4, 8, 12. If you forgot how to use the special right triangle ratio, and let's say we're taking a test or the Regents exam, since it's multiple choice, what you could do is you could use trig. And then you can see which answer choice it's the closest to. So you could definitely use trig here as well to find a side length. I could show you that real quick. So for example, in this triangle over here, let's say I wanted to use the 60-degree angle. So I could do like tangent of the 60-degree angle equals to opposite, which would be the 2 radical 3, over, wait, actually, I don't want to use tangent. I want to use sine because I want to get, it doesn't really matter. But for me, I just want to get the hypotenuse over here because it's an equilateral triangle. So if I know this is 4, I know this is 4. I actually know this whole thing is 4. So 4, 8, 12. So over x, which would be the hypotenuse. And then from here, you can cross multiply x sine 60 equals 2 radical 3. And then we can do 2 radical 3 divided by sine of 60. Let me get my calculator. Oops. And look at that, that's 4. And then each side is 4, so that's 12. So same answer. Okay. Which is the correct equation for triangle ABC? They're all with tangent. So let's check it out here. Let's see. Let's set up tangent for angle A, and let's set up tangent for... No, it's all for tangent of the 25-degree angle. So let's see. It's all using the 25-degree angle. So we have opposite, adjacent. So tangent of the 25-degree angle is A, that's opposite, over 12, that's adjacent. If I cross multiply, it's 12 tangent 25 equals to A, and that's answer choice number 2. In the diagram below of triangle CER, LA is parallel to CR. If CL is 3.5, LE is 7.5, EA is 9.5, what is the length of AR to the nearest tenth? This is what a lot of people do. Be careful. We have similar triangles. 3.5 is not from a triangle. LC is not a side of the triangle. It's a side that's quadrilateral at the bottom, as well as ARX. So I'm going to do it a bit differently. I'm going to redraw the two triangles. The big one and the smaller one on the inside. The big one is CER. The smaller one is LEA. And once I find ER, so I'm going to find ER to be X. Once I find ER, I can subtract 9.5 to get AR because the triangles are similar. Whenever triangle proportionality theorem, whenever you have a line in a triangle parallel to the base, it creates similar triangles. So the two triangles are similar to each other. That's why they told us that these are parallel, so we would know that. Okay, so EL is 7.5. This whole side EC is 11. That's 3.5 plus 7.5. And then I just need to put the 9.5. And now I could make my proportion. 11 corresponds to 7.5. X corresponds to 9.5. Let me multiply. I need 9.5 times 11. 104.5. Going to divide by 7.5. I forgot what it was already. 13.933. But remember, that represents ER. So I need to subtract off 9.5. And that's about 4.4. Okay. Which statement is true? Measure of angle BDC is 100. Measure of angle A is 50 degrees. And measure of angle DBC is 30 degrees. Let me find the other angles first, because otherwise I'm just making up answers here. In this triangle DBC, we have 100 and we have 30. So what does the other one have to be? 50 degrees to make 180. These are supplementary angles. They form a linear pair. So if this is 100, this one next to it has to be 80. And then if we have 80 and 50, the last angle of triangle ABD needs to be 50. So triangle ABD is obtuse. No, it's not. There's no angle greater than 90 degrees. Triangle ABC is isosceles. Yeah, it is. It's got two equal angles. So it's got two equal sides. Measure of angle ABD is 80 degrees. No, it's not. It's 50. I found it. And triangle ABD is scalene. No, it's not. It's got two congruent angles, therefore two congruent sides due to the converse of the base angle theorem. If a triangle has two congruent angles, the sides opposite are congruent. That's converse of the base angle theorem. So answer choice number 2 is the only correct answer. What does angle A plus angle D equal to? Let's use made up numbers as an example. That's what I like to do. I'll just give this a fake value, 50 and 40. That makes 90. 90 plus 90 is 180. So that's a real triangle value. These are supplementary. So if this is 50, this one's 180 minus 50 because they form a linear pair. 130. And if that one's 40, this one would be 180 minus 40 is 140. And now let me add these two up. Let me add A and D here. 140 plus 130 is 270. That's an answer choice. Let me try one more situation and just verify so I could see if it's always true. Let me do 60 and 30. That's 90, 90. That makes a triangle. Over here, 180 minus 60 would be 120. 180 minus 30 would be 150. Once again, 270. In parallelogram A, B, C, D with AC, oops, I drew that wrong. AC needs to be perpendicular to BD. Okay, so here's my parallelogram, and it says with AC perpendicular to BD. So AC and BD are diagonals. I was sleeping before, and they're diagonals. And they're perpendicular, so let me draw that in. So let's ask ourselves, what kind of special parallelogram is this if it's got perpendicular diagonals? Hopefully you're thinking it's a rhombus, and it absolutely is. So we know that AC is 12, and remember, it's a parallelogram. So not only are diagonals perpendicular, but diagonals bisect each other. So if AC is 12, each piece is 6. And BD is 16, so each half is 8. What's the perimeter of ABCD? Start with one of the right triangles. You got two sides. You need the last one. Let's use Pythagorean theorem. The side we're solving for is the hypotenuse. That worked out nicely. And remember, a rhombus has 4 equal sides. Don't pick 10. I shouldn't have circled it. 10 is one side. And notice how it's an answer choice. They always do that to get you. There are 4 equal sides, making the perimeter 40. Read the questions carefully. In triangle ABC, M is the midpoint of AB, and N is the midpoint of AC. If MN, let me connect M and N. If MN is x plus 13, and BC is 5x minus 1, what is the length of MN? Remember that a mid-segment, connecting midpoints, a mid-segment in a triangle is both parallel to the base and half the length of the base. So basically, if I take the mid-segment, which is x plus 13, and I double it, I get the base. Don't equal these to each other. They're not the same. This one's bigger than this one. This one's twice this one. Or you can make your equation to say this is half of this one. But I like to deal with multiplication rather than division. Distribute. And don't pick 9. That's the trick. That's your x value. You're looking for the length of mn. Plug in. Mn is x plus 13, so that's 9 plus 13. And that's 22. You gotta use a compass for this one. They give you 0 points if you don't use a compass, if you just sketch it. And it's pretty obvious if you just freehanded it. So make sure that you use the compass. That way you could practice. Using a compass for the first time on the Regents exam is never a good idea. We need to construct the angle bisector of angle ABC. I'm gonna do with circles because that's how a lot of you guys learned it. But if you don't want to do full circles, you could just do like arcs, pieces of circles, and that's fine too. So what I'm gonna do is I'm just gonna put my compass on the vertex of the angle, which is B. That's the angle that it's asking us to bisect, angle ABC, which has a vertex at B, the middle. Any distance, doesn't matter. Just swing yourself a circle. The only thing that you're interested in here, because it doesn't matter how much you open your compass, the only thing you're interested in is that you got to make it hit the angle in two spots. And if it helps you to highlight the angle so you could see, that's angle ABC. We just need to hit the angle in two spots. Now we're going to go over to each of those intersection points. I'll go over to this one first. And on the computer, you'll notice my construction is not going to be super, super accurate. Try to be as accurate as possible, but definitely if you're doing this with an actual compass, you're going to be more accurate than I am than on this program here. So I just opened up to the width of the intersection, and I'm going to just swing a circle. And then using the same distance, because I am bisecting, I am cutting in half, so I do have to keep the distance the same now on each intersection point. I'll swing another circle. And what you're interested in is where those two green arcs intersect. Those two green, whatever you call them, circles intersect. And right through there is your angle bisector. Each of these angles, here and here, should be cut equally in half into two congruent parts. So if this was a 60-degree angle, which is not because it's not an equilateral triangle, but if it was a 60-degree angle, each piece on either side of the bisector would be 30 degrees now. I'm going to show a less messy version now. We don't need to use all these circles. I'm going to do it faster. Just make arcs. There we go. That was the sped up version. Without the full circles. Less messy. Congruent. Both ways receive full credit. So first, we are translating 5 units to the right. 1, 2, 3, 4, 5. 1, 2. There we go. And now we're oh wait, it was 5 to the right and 2 up. That's not my final coordinates. No. I just read 5 to the right. These are mistakes not to make. Read the question. Don't do what I'm doing and read the question fully. Okay. And now we're reflecting over the line y equals 0. The line y equals 0 is the line where all of the y coordinates are 0. That's actually the x-axis. And let me explain why really quickly. On the x-axis, if I pull any points, right, this point, -6, 0, this point, -1, 0, this point, this point, all of the y coordinates are 0. On the y-axis, all of the x coordinates are 0. The y coordinates change on the y-axis, but the x coordinates are 0. So be careful. The line y equals 0 is not the same thing as the y-axis. The axis where all of the y coordinates are 0 is the x-axis. And you can always just take a couple of points and test them out. If you thought this was what you were looking for, if you thought the y-axis was it, test a couple of points. Oh, sorry. That is the point 0.02. That's the point 0.9. So the x coordinates are 0 here, not the y coordinates. So we are not looking for the y-axis. Okay, so now that we know what line we're reflecting over, let's do it. 2, 1, 2, 3, 1, 2. You're counting to the line 1, 2, 3, then moving an equal distance on the other side of the line. 1, 2, 3. So that is 9. 9, -3. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then finally, 1, 2, 3. 1, 2, 3. Over here, we need to find the angle measurement that the wire makes with the ground. We have a right triangle. We need to find an angle that's trig. Let's do it. I'm going to use sine. And you can always write SOHCAHTOA on. I need the opposite in hypotenuse. Remember, to find an angle, use the inverse. And it says to round to the nearest degree. That's the nearest whole number. What was it again? 30 over 50. And that's about 37 degrees. Okay, here we have the proof. Now, the thing is, on the Regents exam, if you just write your givens, you get 0 points. If you don't write anything, you get 0 points. If you write something that's irrelevant, you get 0 points. Now, when you're looking at the proof, You might not know exactly how to do it, and that's okay. You might not get the full points on the Regents exam, and that's okay too. But we always shoot for at least 1 point. As long as you write one thing, one statement and reason that is relevant and correct, one thing, one valid thing that you can figure out, you get a point. And every point counts because each point brings you closer to passing, or could be the difference between like a 79 and an 80 if you're above passing. So definitely, we want to try to get as many points as we can. We don't want to leave anything blank. We want to try to make sense of it. Now, looking at the givens, we might be like, I don't know how to use these, but I think we all know what this symbol means. Perpendicular, right angles. So if you don't know anything else, at least you know that there are right angles. And we can put that in our proof and get a point, even if we don't know anything else. I'm not going to write all the givens. Actually, I will write all the givens. So once again, 0 points right now. But magically, if I write this, if I write angle CBA and angle DEF are right angles due to the fact that perpendicular lines form right angles, because we did have the perpendicular lines in the givens, magically I can get a point. And not only that, but I know that all right angles are congruent to each other. Now let me read the question. We do need to prove the triangle is congruent. So that already gives me one pair of congruent angles I can use. Great, wonderful. And I already got myself a point here. So I'm doing great on this proof so far. Let me mark the rest of the given so I can figure out what else I need to prove the triangle is congruent. AE is congruent to DF. Oh, sorry, AE is congruent to DB. I said DF and I'm like, wait, that doesn't make any sense. One's the hypotenuse. And AC is parallel to FD. I love parallel lines. Because if I highlight my parallel lines and my transversal, anytime you got parallel lines, you probably have a transversal. And I see a Z. And I know that in the corner of my Z are congruent alternate interior angles. If parallel lines are cut by a transversal, alternate interior angles are congruent. Yes, you do need to put that the lines are parallel. Otherwise, alternate interior angles are not congruent. And look, I'm up to half credit now. I'm doing so great here. Up to half credit. Look at that. You all can get these two things in your proof. After here is where you might get a little bit stumped about what to do next. But up to here, you can all do this. This is 2 out of your 4 points on the proof. If this is a 4-point question on the Regents exam, you're halfway there. A lot of people do this. I want you to think about for a second what the problem with this is. Yes, you're proving triangle similar, not congruent, not similar. And AA proves similarity. You might also be thinking, can't we just use ASA? And we can. The only thing is right now, we don't actually have the full side of the triangle. We only have the piece AE. And over here, we don't actually have the full side of the triangle. We only have the piece AE. So if I want to use ASA, I need the full side in between the two congruent angles. But if I have this piece, I just need to make it bigger. And when we make things bigger, that's addition. Let me write out my addition. Give me 1 second. Let me just clean this up a little bit over here, get a little bit more space. Let me think about what I need to put onto AE to make AB, because ultimately what I want is AB, the full line segment. If I have AE and I put on EB, then I get the full line segment AB. And on the other side, I want to make DE. I have information about CB. And let me think about what I can put onto CB to make the full side CE. And that turns out to be BE as well. You can also write it as EB. BE and EB are the same segment. In order for our addition to work, we have to make sure that we're starting with two congruent segments and adding on two congruent segments for our sums to be congruent. We are starting with two congruent segments that was given to us. But are the two segments that we're adding congruent? Well, yeah, EB and BE, they're the same segment, right? EB, BE, they gotta be congruent, but that's not in my proof. So before I can do my addition, I definitely need to say that BE is congruent to itself. And you don't even have to reverse them. You could just say EB is congruent to EB or BE is congruent to BE. That's fine too. And that's due to the reflexive property. And now your addition's valid. Substitution always follows addition or subtraction because this plus this is this. AE plus EB literally is AB. You're replacing this, you're substituting it with something that means the same thing. CB plus BE is CE. You're replacing this with what it actually is. You're substituting it with something that's equivalent. And now we have the full sides AB and DE. So if I just, to show you clearly what the point of this was, if I just redraw the triangles really quick for you. What we have now in the two triangles I'm like staring at this and I realized I put the right angle in the wrong spot. The right angle is at angle E. I'm like, why is it not in between? And now you can clearly see that what we have is ASA. Angle, side, angle.